The vectors v1 to vn form a basis of the vector space V if and only if two conditions hold. The first condition, this set of vectors, they are linearly independent. And the second one, they span the vector space V. So to be able to form a basic of the vector space, these vectors need to be linearly independent and they need to span the whole vector space. So there are two conditions. So the standard basics of the Euclidean vector space, say R3, is a set of three vectors E1, E2, E3. So E1 is 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. First, they are linearly independent, and second, they span the whole vector space R3. So here we have another example. Do the following vectors form a basic of R3? E1, E2, E3 are these vectors, and 1, 2, 3 transpose. So another column vector here. And they don't form a basics of R3 because they are not linearly independent. They linearly dependent, so they do not form a basics of R3, right? Because we know that, okay, we just need three vectors, in fact, and here we have four vectors. So later on we will learn that this is the Euclidean vector space of dimension 3. So the maximum number of linearly independent is 3. Here we have four vectors, so no matter what, they must be linearly dependent. So here's the second example. Say 1, 1, 1 transpose. So we have the column vector 1, 1, 0 transpose, and the last vector 1, 0, 0 transpose. So there are three vectors in R3. So we need to check two steps. Step 1, check if they are linearly independent or not. And the answer is yes. And the second step, we need to check if they span R3 or not. And the answer is yes. And you know how to check these vectors are linearly independent, right? So for the first step, check whether they are linearly independent. We consider the system equation C1 vector V1, this is vector V1, this is vector V2, and this is vector V3, say. Now consider this, the linear combinations, say C1 times vector V1 plus C2 times vector V2, C3 times vector V3, 0, 0, 0 transpose. And we check if this system, so here this is a system of equation with three variables, C1, C2, C3, right, and three equations. And we check if this system has only the trivial solution. So from here you can do three ways. So because we have three vectors, so we can first, the first way we can just check whether the matrix, this matrix with three column vectors, the first one, second one, third one, this 3 by 3 matrix is invertible or not, right? By computing the determinant. And if the determinant is non-zero, then they are linearly independent. The second way, we just solve this system equation. Implies C1 equal to C2 equal to C3 equal to 0. Yeah. So here say form C1, C2, C3 are scalar in R. So implies C1, C2, C3 on 0. This means that they are therefore they are linearly independent. So that's the first step. So I'll write here the other way. Another way to check that. So let's say matrix A is a matrix 1, 1, 1. The first vector, put it on the first column. Second vector 1, 1, 0. The last vector 1, 0, 0. Matrix A has determinant of A is non-zero. And this implies that A is or equivalent to A is non-singular or invertible. Implied equivalent to 3 vectors, or this system has only the trivial solution. Imply that the 3 vector linearly independent. Okay, so this is the first step, checking the vectors are linearly independent. The second step, checking whether the vectors span R3. How to check that? So this means we need to check if any vectors V in R3 can be written as a linear combination of 3 vectors, say V1, the first column, V2, and V3 or not. V1, V2, V3 or not. So let me put here V1 is this vector, V2 is this vector, V3 is this vector. So this just means that now we have a vector V, say V is of coordinates, say x, y, z in R3. Check if they exist. They exist, say A, B, C, real number such that V equal to A times V1 plus B times V2 plus C times V3. So V is x, y, z given to us, right? So we are given this V. We check whether V can be expressed in terms of linear combination of the 3 vectors. V1, V2, V3 we know. So what is V1? V1 is, okay, this vector, so this is this matrix. It just means that times ABC, right? So we have that. Okay, we know that, okay, by the second method, say we know that matrix is invertible. That matrix is invertible. Then this system has unique solution. So say star. Since A, this matrix system star has a unique solution, say that is A inverse times this vector, right? So this ABC is a vector with all these variables ABC, right? So and this is the system x, y, z given to us. So ABC equal to the inverse of this matrix times this vector. Which is this matrix inverse. So ABC times this vector. And therefore we can always find ABC to have this equality, right? So V can always be expressed as a linear combination of three vector V1, V2, V3. Therefore V can be written as a linear combination of V1, V2, V3. And in other words, we prove that. So here for any V, so V is chosen arbitrarily in R3, right? So V1, V2, V3 span R3. So two conditions are satisfied. The first condition, they are linearly independent. The second condition, they span the whole vector space. And hence V1, V2, V3, this set form, or they form a basis, this set is a basis of R3. So I have a comment here. Because we are given exactly three vector in R3. So the number of vector here equal to the number of dimension of the vector space. So in fact, one condition is enough. If they are linearly independent, then we can conclude that they form a basis of R3. But that's for later theorem. So if we are given three vector in R3, we only need to check the first condition. The second condition automatically corrects. Because if we check the first condition, they are linearly independent, it means this matrix is invertible. And because this matrix is invertible, we can always find a solution, ABC, right? The inverse of matrix times XYZ. Therefore, XYZ or vector V can always be written as a linear combination of three vectors. And therefore, the second condition is always correct. Vector V in R3 can be written as a linear combination of three vectors. Or in other words, they span R3. Okay. So, just say it again. Three vectors in R3 are linearly independent, then they form a basis of R3. Now for the moment we use definition, so we check two conditions. The first condition are linearly independent, the second one is span the whole vector space.